So we're meeting all, and at this time, I'm going to turn it over to Mr. Smith, who's anxiously awaiting to show you guys some demonstrations. Thanks.
Okay, very good. Well, it's great to be here, and it's great to have you all joining us. So we're going to do a little bit of a virtual lesson here with some solutions. I am here in my lab in room 802, so you'll see I'll move the camera around a couple times to show some of the demos that we have, and definitely feel free to ask any questions at any point. So that'll be great. It's a pleasure to have you all here tonight, and thanks for watching. So hopefully this gives you a little bit of an idea of what the online experience can be for us here during our virtual school, and also a little bit of an idea of what happens in chemistry your sophomore year. So at this point, what happens as a freshman is you'll be taking biology. And that's the study of life. So you have, Mr. Fletcher, of course, can chime in at any point. Me being the chemist, he being the physicist. But you're studying cells and organisms and the organization of life and so on. So what I'm going to show you here is what you would encounter your sophomore year. I teach chemistry, and also when we have AP chemistry, I teach that as well. So I look forward to seeing some of you when you come into 10th grade. Okay, so what I'm going to do to start things off is we have this function to share the screen. And I'm going to bring up a PowerPoint presentation that I have. And I'll kind of go back and forth between the PowerPoint presentation that I have here and showing you a couple of demonstrations. So let's take a look. So our topic for today here is solutions and solubility. I'm just going to do a technology check real quick. Maybe Mr. Fletcher, can you see my screen okay where it says solutions and solubility?
Yes, I see solutions and solubility on a white screen. Yep.
Okay, excellent, excellent. So this is actually, Mr. Fletcher helped me out with this a couple years ago, the fall of 2017. And I'm going to call this sodium iodide solution in action. Now, the truth is the solution part, which we use a lot of solutions in chemistry, but the solution part is almost just something to get this reaction going. But we'll focus on that a little bit more in a moment. But take a look at this here. So I'm pouring a solution into the pumpkin. This was in October, of course. And yay, there we go.
Yeah, it looks like an exothermic reaction there, Mr. Smith.
Absolutely. Yeah, a lot of steam coming out. Definitely exothermic. That term is going to come up in a couple of minutes here. But if I can back this up just for a second, and we'll actually see something that's, like I said, not the main attraction of the demonstration, but if you see right in there, this is the solution, and you notice that it's clear. And that's going to be something that we refer to here in a couple minutes. So we have a clear solution, and many of the solutions that we have are clear as a starting point. Okay, can you see me? If I hold something up, can you see me off to the side?
I can see you in the bottom. The bottom has a little panel.
Okay, so it doesn't have to be too big, but you can see a little bit of, this is actually just some sodium chloride that's there. And you can see the crystals of the sodium chloride. As it turns out, the sodium iodide that I used in that demonstration is very similar in terms of what it looks like. So when you have a substance dissolve, we say that it disappears, or at least what it looks like. If you're putting some salt in water, it's dissolving because it basically disappears. You don't see it anymore. And the same thing with sugar. You could taste it for sure if you were to try it, which we don't do often in the lab, obviously. But we do see it disappear. And I'm going to do something a little bit later on, assuming that things go well for us, to illustrate this here, where we actually have a gas that's going to be disappearing in a solution as well. So we have this idea that when something dissolves, it disappears. One of the big topics or the big skills that you have to do in AP chemistry, which is usually your junior year or your senior year here, is to be able to connect what we say the macroscopic to the microscopic. The macroscopic is what you can see. Off to the right here, you can see the picture, and that's what salt would look like. The microscopic is actually even smaller than microscopic. Is going to be over here where we see what's actually happening down at the particle level, where you have the sodium and the chloride that are building on each other and then making up this crystal that's right here. So I'm gonna now, if you were to look, you can see in this picture, you see this tiny little crystal that's down there?
Yes, I see it.
If you were all here, I'd have you take a guess as to how many sodium atoms you think might be there in this tiny little crystal that's right there. And I did a calculation earlier, and it turns out that there are 5. I'll start adding some zeros. There we go. This is approximate for sure, but there are approximately that many sodium atoms in that tiny little crystal that fell off the side of that pile of salt. So these are really, really small. Now, when something dissolves, back up for a second, it's actually going to separate, and it separates. In this particular case, we have the sodium chloride is going to separate into sodium ions and chloride ions, and they're going to be surrounded by water molecules. Okay, so we'd have the H2O molecules that would be getting in here and surrounding all of these particles here. And the same thing would go over here. So that's why it disappears in a sense. Because now instead of making up that big crystal, or that small crystal, but a large number of those ions, they're now separated and put into the solution. And that's why we don't see them anymore. So all these water molecules coming in here. Okay. Now there are some limits. If you were to look at this test tube over here, and if we wanted to put a spoonful of sodium chloride, it would probably dissolve. Maybe 2, but as you can imagine, we wouldn't be able to pour a whole canister in there. We would have a limit to how much would be able to be dissolved. And so we're going to consider a little bit the limits of solubility. So as you put the salt in a short amount of time, it's going to dissolve. And so we'll go ahead and erase it. So then you would see that it would basically look like a solution, and we're familiar with that. But eventually, what would happen is that it would get full. And so we would be adding in this solute, and then eventually there just wouldn't be enough water molecules to pull apart those crystals. And so we'd start to see it build up at the bottom here. And we'd say at this point, we say the solution is saturated. Saturated meaning that it's full, that no more can dissolve. Now, if we didn't quite add as much, and if there were still more room that it could dissolve, then we'd say that it is unsaturated. There's still plenty of room in this solution for more solute to dissolve. Now, you might guess that those are the only 2 options, but there is a third option here. We have full, we have not full, and now we have, as it says here, there's more than full. And so as you might guess, anybody want to try to wager a guess here? You can maybe unmute and guess what this would be. Not unsaturated or saturated. What might this be where you have more than saturated? So we'll bring it in here.
Somebody raise their hand.
Oh, okay, yeah. I don't see it. How can I answer that?
Who is it? Maggie McGrath. Whoever's that.
That's me.
All right.
What do you think?
I'm gonna say overly saturated.
Oh, great guess, but not quite. Yep.
Okay.
Same idea. What we use the term super meaning past there. So we have supersaturated. Okay, and so that means you actually, it's more than full. So supersaturated solution, but thanks for your guess. Now, what would that look like here? I'm going to show it to you for real in a second. We might think, well, maybe there'd be lots of particles in here. But as it turns out, a supersaturated solution looks the same as an unsaturated solution. But we don't have any particles building up at the bottom, which is kind of interesting. I'm going to show you that in a second here. Okay, blank screen. Uh-oh, here we go. Time for our first demo. I have a supersaturated solution of sodium acetate. So I'm going to stop the screen here. Maybe, Mr. Fletcher, can you verify, is it back to me?
Yes, you are. I see you in your lab right now.
Okay, very good. So I'm going to turn the screen over to here, put my goggles on.
And actually, Mr. Fletcher, can you turn your camera off for just a minute? That way he will...
Yes, absolutely.
Okay.
There we go. Is that better?
Yes, thank you.
Okay, you're welcome.
Okay, so here in the test tube, I actually have a supersaturated solution. And I'll bring it up close, and you can see that, actually, it's just starting at the bottom. I think I'll grab another one. You can see that it's pretty clear. There's not really anything building up on the bottom, so it looks just like the other ones. Now, you'll forgive me for making you wait that long for the exciting part, because if we take a little piece of the crystal and we drop it into the supersaturated solution, see what's happening.
That is cool.
So now it's we'd say it's crystallizing out. Because remember, supersaturated is too full. So it realizes when we give it a little place to saturate out or to crystallize out that, oh, wait a minute, I need to, oh, and then we turn it upside down and then it doesn't come out. Unfortunately, I can't pass this around for you to feel the test tube, but it's quite hot. So that's an exothermic process right there. Kind of looks like it's frozen, but it's actually quite hot. Now, since I have another test tube, and I don't think I'll need it till next next fall, so we'll add that in again. I use this demonstration actually early in the year to illustrate the idea of polyatomic ions, which are ions like sodium and chloride, but they have more than one atom. And the idea of being unstable, because this is just waiting to change, just waiting to crystallize out. And you can see it goes all the way to that. Okay, so we'll go back to the presentation now. So that was our supersaturated solution of sodium acetate. So the question,
yeah, I can see your screen now. Supersaturated solution. Yep.
Perfect. Thank you. So as supersaturated solution, we might think, well, how do you make that? How do you make a supersaturated solution? Unsaturated, you just put a little bit. To saturate it, you look and see until there's some crystals building up at the bottom. So for a supersaturated solution, we might think, well, you just kind of keep on dissolving something in. But the problem is that that'll just keep on making it saturated, and we would never get to supersaturated. That's what that says there. So the key is going to be temperature. That's the key in order to make these supersaturated solutions. And here I have what's called a solubility curve of sodium acetate. And I'll get this here. So what this shows is the combination of temperature and the number of grams, which is going to saturate a solution. So the idea is that right about here, we would have either saturated or unsaturated, and then we let it cool. And then as it cools, it wanders above the line and then ends up in the supersaturated region. In fact, right now it's about 25 degrees Celsius or so. So it's probably way up here. Then we give it a chance to crystallize out, and it's like, oh, this unstable solution changes. And so it drops down to here and then continues to crystallize out. And that's the crystallization that we see. Okay, so this is a few other substances. This is actually the sodium acetate right here, and you see a whole bunch of other substances. If you remember that, that sodium iodide, actually potassium iodide solution from early on with the pumpkin that I poured into the pumpkin, that's it right up here. So you can really dissolve a lot. So this shows the grams that you can put in there, and then we see how it changes with temperature. This is one of my favorites here, potassium nitrate. Potassium nitrate, also known as saltpeter, it's used in black powder for setting off fireworks. Of course, it was used in muskets and cannons. And so the solubility turned out to be very important in order to be able to crystallize out pure potassium nitrate. It changes very drastically. Okay, so that's our solubility curve. Now, as you would see, many of them would have a higher solubility when the temperature goes up. And we could talk about being endothermic or exothermic. Some of them will get quite cold when you put it in water. However, the gases will decrease in solubility when the temperature goes up. And that's because when they dissolve, they're actually exothermic. And that's really a topic for AP chemistry. So we'll discuss it more in about 4 years or so, 3 or 4 years, 3.5 years, I guess. But if you look here, you see this NH3, and we see how this line is actually going down. So as we increase the temperature of NH3, we can dissolve less. And as we increase the temperature of SO2, we can also dissolve less. Whereas these are going to be solids, and they go up. Okay, so ammonia goes down, HCl, if you put it in water, that's hydrochloric acid, that also goes down. Okay, so here we go. Our next demonstration is the off-gassing of ammonia gas and the ammonia fountain. So we'll go ahead and stop presenting here.
Yeah, you're back in your lab.
Okay, very good. A student asked me this year if I ever got nervous during doing demonstrations. And I said yes, every time. Sometimes just being nervous to see if it works. I was glad that this one worked out. It's always, kind of keeps the excitement here. But this is some concentrated ammonia solution, and it has quite a strong smell to it. What I'm going to do is pour it into this flask. I'll move it down a little bit. And I'm going to heat it with the Bunsen burner, and we're hopefully going to be able to see that it's able to, what we say, off gas, meaning that some of the ammonia will actually come out of solution. It looks like it's boiling, to tell you the truth, because we have the liquid and then it starts bubbling. But it's actually just off gassing. It's a similar idea to what was happening with that sodium acetate. Okay, so I'm going to light the Bunsen burner here. Oh, and you see quite quickly, actually, it starts bubbling. Can you see the bubbling?
Yep.
Yep.
Yes.
Okay.
Yes.
Now, you might think that it's boiling, but that's actually just all the ammonia that's coming out of solution. And coming out, I actually turned off the Bunsen burner. And it's filling this flask that's over here. A little bit of water vapor, so that kind of made its way in also. Now, as it turns out, the ammonia is less dense than air. So even though it doesn't have a container on it, doesn't have a stopper, it should stay in there pretty well. Okay. So I'm just going to double check to see you can see everything. So now what I'm going to do is I'm going to squirt some water up into it, which hopefully will allow some of that ammonia to dissolve. And then there we go.
Oh, that's cool.
Quite vigorously, actually. and we're still working on the manners, but so a little slurp at the end there. Okay, so a couple things are happening. A little bit of acid-base chemistry with the pink that happens. But what I wanted you to notice is that just like a solid will disappear, we can notice that about 2/3 of this gas actually disappeared. This was full. I had no way for the gas to get out. There was only liquid going in. And so just like a bit of sugar dissolving in water, the gases will also disappear and go into solution there. So a few things going on with that. Does anybody have a question at this point?
No, this makes sense.
No, I'm trying to fix my Bluetooth.
Okay, very good. All right. So moving along here, we have the solubility curve. Just a couple of questions to finish things off. I'll actually get this out of the way. These are the types of questions that I would ask on this topic. How many grams of potassium nitrate does it take to saturate a solution at 20 degrees Celsius? So if anybody thinks they can answer that, feel free to answer it in the chat or so. I can't see it, so maybe Scott or Andrew, if you see an answer, you feel free to let me know. But we have potassium nitrate.
Oh, we got Adrian. If you want to unmute, you can definitely talk. I see you raise your hand.
What do you have, Adrian?
Oh, maybe not.
Okay.
Oh, it's in the chat. Hold on. There's a. She says 38 grams.
38 is pretty good. Yeah, well done. Well done. And who answered that?
Adrian.
Adrian. Okay, excellent. Yeah, we'd go with 20 degrees Celsius. You go up to the line, and it's probably right around here. So that's kind of in the 35. You know, definitely would accept a 38 grams. Okay. That's one way you can look to the graph and get information with this. How many grams of NH3 will dissolve at 20 degrees Celsius? So we now go to ammonia, a different substance. This is what looked like it was boiling, but it was just off-gassing as some of those bubbles were coming out. So we come to about here, and we'd probably say about 56 grams or so. NH3 at 80 degrees Celsius, you can see is going to be much less. So we come out to here, and it goes from approximately 55 now down to about 12. And so this is by heating it up. That's how we got the ammonia to come out and fill the flask. And then maybe with this last question, we'll see if you guys can answer it. So let's say you have potassium nitrate. So we're looking just at this line. We're at 60 degrees Celsius. And it turns out that there are 80 grams dissolved at that temperature. So that's going to be right about here. Remember, we're only referencing this blue line. Is that going to be unsaturated, saturated, or supersaturated? So Mr. Seelig or Mr. Fletcher?
Simon has the answer. Simon, do you want to unmute?
Yes, Simon. What do you have, Simon?
Simon said saturated.
Simon, saturated? No, not going to be saturated because that's going to be on the line. So since we have 80 grams and it's at 60 Celsius, it actually lies below the line. So that's going to be unsaturated. Saturated would be right on the line, actually. But thank you for answering. Okay, so we'll give it another shot in about a year and a half when you guys are in my class and here in room 802 and we're studying solutions. But at least you could get a little bit of an idea of that. Okay.
Well done.
One last demo here for you. Mrs. Fusco took this picture. This was at our graduation parade. And this is definitely a solution demonstration here where you had some soda and the bubbles were coming out of solution. So another example of off-gassing. So I'm going to show that to you. But to tell you the truth, not being outside, I think I'll do I'll call it a half charge. So not quite as many Mentos in this here. Okay, so hoping you guys can see the fish tank. Can you see the fish tank?
Yes.
Yep.
All right, so here are the Mentos, and we're gonna put them into the Diet Coke. I must confess I'm gonna move my bag out of the way just in case. And in case you're worried, I do have a big roll of paper towels just in case off to the side. And I need them not to go in too quickly, so I'm gonna use these. These are detention slips, and the good news is that I tend to use them for extra stuff like this more often than detentions. I made a mistake earlier in the year. I was walking towards a student during class, and I had the answer to a question on the back of a detention slip. And as I was walking towards her, she was afraid I was assigning her detention, so had to clear that up. Okay, so as I pull away the detention slip, the Mentos will fall in, causing the carbon dioxide to come out of solution, and then hopefully having a fun effect.
Perfect. Well contained.
Very good. Well, not too many paper towels needed. Okay, well, thank you for your attention. If you have any questions, of course, let us know. But thanks for watching, and look forward to having you all in chemistry in a couple of years.
Thank you, Mr. Smith. And we got a few people saying awesome, good job. We are going to switch it over to Mr. Fletcher now.
Okay, well, welcome, class of 2024. I have a little iMovie I'm going to show you at the end. Let me see, can you see this right now? I'm going to start off with waves. I'm going to do something regarding waves, and it was basically, let me see if I can get started up right here. And we're going to do sound waves first, and then we're going to get into light waves, lasers, and such. So while we were in virtual school the whole time, the students did a great job knowing how to navigate through Teams and all that. So we're going to be using this type of structure here. This is something we use. There's a PHET, P-H-E-T, from Colorado. It allows you to do all these little interactives. And there's also another one, Physics Classroom Online. And can you see this online tone generator?
Yes, we can.
Okay, thank you. So students, you'll get very used to this. Can you hear that, Patrick?
Yes, yep.
Okay. So our passing bell, we figured out my name's Mr. Fletcher. I teach honors physics and the astronomy. So between Mr. Smith and I, we're representing the physical sciences. So when we get to sounds and waves, basically what is a wave? It's a disturbance in a medium. And there's two types of those. There's electromagnetic, like lasers and sunlight, which move at the speed of light. And there's also mechanical waves, which require a medium, like sound can travel through solids and liquids and gases, but they need that medium in order to translate that kind of energy. So coming from our speaker system for every passing period, you'll hear this at 516 hertz. That's our passing bell. So it's kind of fun getting to that. Now, there's hearing tests we can do too, and hearing tests allow you to start from very, very low to very high. So I want you to help me out here, all you people. And Andrew, you can help me out. I want them to raise their hand when they can no longer hear this. This is going to be it's going to start at 0, very low frequencies. And then I'm going to go ahead, and when you cannot hear the sound, then I want you to put up and to show you why, as adults, basically how human hearing works. You have a little tympanic membrane deep in your ear, and as pressure waves come in, it vibrates it, and it's just an amazing thing how those nerves in your brain we can communicate. It's just like magic, really, when it comes down to it. So as you get older, the wear and tear on that, you can't hear as the higher frequencies. So I'm going to raise my hand somewhere around 12,000 hertz. But students like yourselves, you'll be up there in the 15, 16, and some of you maybe even 18,000 hertz. So if this is bothering you, just put your fingers in your ears at the end. So here we go. So here it is. It's saying now what a hertz is how many waves per second. So right here, we're approaching 3,000 waves per second right there. That's what a hertz is. How many vibrations per second, VPS. We're at 5,000 vibrations per second. And it's kind of annoying right now. We're getting up near mosquito wings batting away. 7,000, 8,000. Now, right around 12,000, it starts getting choppy at my age right now, so it can't vibrate. It's not as sensitive. So I'm going to raise my hand right now, so just under. So, Andrew, you're on your, just let me know if you start seeing hands go up, and it should be about.
I'm starting to worry about my hearing, Mr. Fletcher.
Okay, we're at 15, 16,
hands
17,
up.
18, 19, and we're going to stop right here. Now, human hearing range goes from 20 hertz, a very low frequency, to 20,000. And that's like right out of the womb. So, these poor babies, when they go into this room with all the computers and things, they hear that, which we go deaf to very quickly. That high frequency really disrupts our nerves, and it goes downhill as time goes by. So, babies at first, no wonder they're screaming. They're hearing 20,000, 19,000. That's very, very annoying. There's different other things called the binaural beats. And what these are is if I play one frequency over here at 500 vibrations per second, and I put another one over here at 3, well, here, I'll initially do them at both 500. You'll hear this. Well, you don't hear any difference. Now, the reason is because they're both vibrating exactly at that same frequency. Now, as this number gets higher, the pitch goes up. As this gets lower, the pitch goes down. So if I make this one just one frequency, 1 hertz different, what happens, you're going to hear what I call them woo-woos. You're going to hear one oscillation per second. Now, see if you can hear this, because the difference between 500 and 501, you should hear one like woo-woo. Right? And if I do it till, I don't know, 4, we should hear like 4 woo-woo. Oh, so what just happened here? We'll hear 4 woo-woos per second. So here we go. Play. 4 woo-woos per second. And then you guys will get it as I do this. We can go 520, and it's going to be hard to hear 20 vibrations per second. But that's what happens right there. So I'm starting off with sound waves. So sound waves, they do require a medium. And so if this is a speaker system that we have right here, and we were to start it, it's going to start pulsing. And you can see this little diaphragm here, and you could easily make your own speaker. It's not very hard. We do it in our science physics class. And as this vibrates back and forth, as it goes forward, it's pushing or compressing. It's compressing the air. What is it compressing? Air molecules. So the more dense the air is, the more energy that gets to be pushed out. And as it goes back, they call it rarefacting. So one way it's compressing, and the other way it's a stretching. It's a fancy way of saying rarefacting. So you can see these oscillations here. So it goes forward. You can see these crests and the troughs. And you've all seen a sine wave with a crest and a trough. You've all gone to the beach. And a wave is a wave is a wave. If you go to the beach, the disturbance in the medium is the oceans, right? And as you go and you put your towel down at the beach and you swear to God, you walk straight in, and you go and you play out in the water for a bit, and you swear to God you came straight back in, but your towel's down there. And there's a reason for that. They're called longshore currents, because as those waves approach the shoreline, they're grinding on the seafloor there and they're slowing down. So anytime any wave slows down, they call that refraction. That's called a refraction kind of indice right there. So that's one wave slow down. There they can do refraction. Now in air, in our air that we have right here outside, we might be, if we do Celsius, it might be like 80 degrees, 70 degrees. But if I use Celsius at 0 degrees, so in wintertime, if it's freezing, 0 degrees, the speed of sound is 331 meters per second. Now think about that. So that's 3 1/3 football fields. I always try to have my students go, well, what if I could color that kind of pulse wave, that energy? So if I went like this, and they were standing about 4 football fields away, and they see me, and if I go like this, they could maybe I can make my sound clap colored blue, and it was 0 degrees out, they'd see it, and 1001, it would go 3 1/3 football fields, right? So as temperature goes up with the speed of sound, the sound gets faster, and it gets 0.6 meters per second faster, right, for every 1 degree Celsius. So, it gets faster and faster and faster. And there's a reason for that, because as temperature goes up, as you all know, in the wintertime, when it's colder, it's very dry. There's not a lot of moisture in the air. So speed of sound is slower. But as temperature goes up, there's more and more water in the air, humidity. And as you get to that state of matter, it's more dense. And if it's more dense, it can translate this information right here much, much faster. In fact, if it's 331 meters per second in air, it's about a mile, 1,600 meters in water. With the same clap, if I went clap like this, and you may have in your travels and playing around, clap two rocks or two hard substances together in a pool, and it sounds like it's right in your ear. And the same thing if you've ever gone wakeboarding or water skiing. If you wipe out and you're under the water, it sounds like the engine's right above you, the props. It's kind of scary, but then you get up quickly because you're kind of panicking. You see the boat's like 200 yards away. Hopefully they come back, right? And in steel, it's about 3 miles. So if you put your ear on a railroad track and someone pings it with a hammer, in that same 1001, it would go 3 miles in steel, and that same 1001 would go 1 mile in water, and in air, 3 1/3 football fields. Okay, so when we do this, I'm going to show you another one here and get rid of this guy here. This is how the pulses all work. And how I also illustrate this is I built what's called a Rubens tube. Now, this one here is some Australian guy, and he built it. Then I'm going to show you one that one of our Chinese students actually recorded with me. She loved it so much. She goes, Mr. Fletcher, before I go back to China, can I record this? And how this is going to work here, I'm going to take out the sound for him. And this is a tube that I built, and he has one obviously as well. And I drilled 150 holes into it. So it's like 150 birthday, candles. And on one end, I put a little balloon, and that's where I put a speaker. And the speaker, once it starts playing like a pure tone, like woo, it's going to vibrate that back and forth. And just like I said, compressions and rarefactions, where it compresses, more gas will be pushed out, because on the other end of the tube is where I pump in propane. So one end just has a flimsy, balloon, so it's not going to be like a big pipe bomb or anything like that. Now that's what would happen right here. Let me freeze it right here. Now what's going to happen right here, as you have compressions and rarefactions, velocity equals frequency times wavelength. And we know the velocity, right? Because we know the temperature, we know the velocity. So we can put a certain frequency on one side, say like 1,000 hertz, and then we can just simply solve for the wavelength. And you can just measure it. I actually take my meter stick and I measure it, and we can do that. We'll measure it in centimeters and convert it to meters, and we can prove that what the speed of sound is. So right here, this is a pretty high frequency. Right here, let me see if I can. See, as he goes lower and lower, the wavelengths have to get longer and longer, right? See, and that's one. One doesn't even show up on there. So that's one Rubens tube. And let me see if I can find the other one that I had here. No, not that one. Hold on here. Hold on. I have it right. One of my friends here, right there. Let me bring this up one more time. And that's when we get into lasers and things like that. Well, I've lost that one, but we basically, when we get to do sound, we do all kinds of sounds in different temperatures and record the velocities and the wavelengths. So what I'm going to do right now is I'm going to switch over to the electromagnetic waves. And here's one of the things we did this spring here with electromagnetic wave. And electromagnetic waves move at the speed of light, so it's much different than the 331 meters per second. They move at 300 million meters per second. So when someone says, the speed of light, the speed of sound, whatever, it's a huge whatever. It moves 1,000,000 times faster. So whereas your 1001 for a speed of sound at 0 would go 3 1/3 football fields, 1001 with light, if you could bend it around the Earth, would go around the Earth over 7 times in the same 1001. And we know sunlight from the sun to the Earth takes about 8.2 minutes, right? At that crazy, crazy speed. So we're really seeing like old light. It's already 8.2 minutes old. So what I do with one of my classes, I take this thing called a diffraction grating. And we have a meter stick. And what we do is we take 3 different lasers. I have a red laser and I have a green laser. You can see it. There's my red laser. And then I have a green laser. And then I have a violet laser. And as you go from red, green to violet, or you guys know Roy G. Biv, right? You go from the longer wavelengths, red, to the shorter wavelengths, violet end. So Roy G. Biv. So you're going from crests being far apart with red, and then Roy or orange, right? Yellow, green, blue, indigo, violet. So they're moving all at the same speed. So when you go from a red laser to a green laser, it gets much more energetic. And even though the violet laser doesn't look all that bright, And there's a reason for that as well. It is the most powerful, because if you were to squeeze these little crests just a little bit more, you get something which is called above violet, and that's called ultraviolet, and that has so much energy it can burn your skin, right? And on the other hand, we have red. You can see how the space dots right here, right? This is like a little demo that we did. They're much farther apart. And if we were to just somehow, if you had special glasses and I could physically take those two dots, and if I stretched them a little bit more, it would be longer, and it'd be below red, and that's what we call it infra. Infra is a prefix for below. So below red, infrared, then it jumps into red, and then we go through the Roy G. Biv, and then above violet, we have ultraviolet. So how this whole thing worked, we put a diffraction grating, this little guy here, right? We just supported it on a little like ring stand, and we put it 3 meters away from the wall in my room. Now, 3 meters here, and then we did it with a green laser and then a violet laser. So we sent it right through this exact, what is a diffraction grating? It's a piece of plastic where the lines are so close together, right? When I was in high school, we used to make our own diffraction gratings. We'd take a biology slide and we'd smoke it with a match so it got all sooty, and we'd take a bunch of razor blades together and make our own strands, and then we'd have to measure them. But we buy them so they're super accurate. Now this one says 600 lines per millimeter. So that means per millimeter, there are 600 of these lines. Pretty fantastic, right? So when they go through there and we use the same diffraction grating, it separates, it diffracts the light to this spacing. And then green, it's a little tighter, then violet, a little tighter. And we can measure that distance and plug it into a formula and figure out velocity, frequency, wavelength, and such. So you may ask, well, Mr. Fletcher, why is violet light doesn't look as bright as green? And green is by far the brightest, and so there's a reason for that, because when, all the suns in our, universe here, and in our galaxy, and in our galaxy, we have our, a yellow dwarf star. It's called our sun. And so there's all different types of stars. There's red giants and white dwarfs and all. We happen to have a yellow dwarf. And out of all the trillions and trillions of stars, every one broadcasts its peak in a certain frequency. And it just so happens that our sun broadcasts in the green. It peaks not only in the visible light, but in the green, the Roy G of the Biv. So our sun peaks in the green. And so as that happens, that's why it's kind of interesting to see that, like, we have green grass. We have green leaves on our trees, right? And that's the reason why. If we were around another star, and there may be many other stars that peak in the red, and they'd have red grass, and they'd have red leaves on their trees, or violet, and violet. Like Mars, when they go to Mars, it's orange. It has an orange hue to it, the red planet. All right. So that's one of the things one of the labs that we do with the lasers. Now, I'm going to get down here, and I can use this, and then we go back to this here, and I get back to this, and here we go. I'm going to get rid of this guy and this guy, and I'm going to bring up all these guys. Okay, so with the lasers, and this is how we did our virtual school. I use this PDF annotator, so and it's kind of interesting to see all the. Oh, it's still loading for some reason. There's some pause. Uh-oh, it's still loading here. Let me see if I can pick it up. Oops, did I lose everybody?
No, we still have.
Oh, you can still see me? Okay, these things, let me see if I can bring it up again. Oh, okay, so it's not loading on my end here. I had them all set up here. Well, let me see if I can pick something else up here. Let's see. Okay. So right here with this light here, we do something which is called Snell's Law, and I give students a green laser, and the green laser, this is like 500 nanometer wavelengths. Now, what they do is they have a glass block, and what they do with a glass block is they take a laser and they fire it right at one of the sides of the block, and you'll see, like, it not only as it goes through the glass, as you know, light can go through glass, it refracts, and anytime any wave slows down, what do we call that? Refraction, just like at the beach, any wave. But you'll see it also has a quality where it can reflect. So as it comes in at this certain angle, and how do we know what angle this is? Well, we take what's called a perpendicular to this face of the glass, and we make a perpendicular, and we go all the way through into the glass, and that's at 90 degrees. And we measure it, and they call that the normal. So we measure to the normal. So if that was 30 degrees and we were doing a mirror, this would reflect that 30 degrees because the angle of incidence, incoming, equals the angle of reflection, the reflected light ray. But this whole lab here had to deal with a refraction and what's called Snell's Law. And we know that we could figure out how fast, by firing a light into glass, how fast that light travels inside a more dense material. For example, here it is at air, and it clearly refracted through, and then it came out here. So I'm going to let this run for like 30 seconds, what it is. And this is me. You can see it reflecting. I'm trying to use the laser, and I put a dot right where it goes in, and then a dot right where it hits it. Now, as it goes through, I'm putting another dot here, and then one more dot I'm going to put way out here. And then I'm going to do it with a triangular piece of glass, and then we're going to take it off, and you can see how we're going to actually figure out what's called Snell's Law. So it's different interface here, but it's the same exact principle. You have a perpendicular, but it's not like a square where you have the 90 degrees. You know, people get kind of confused with this. You can kind of see it. It goes in here, and then it fires its way through here, and then comes out here. We're not doing mirrors or reflections. We're doing refractions. So you'd find it there. You put a little dot right there as it traveled through the glass here, and then one more here, right? But remember, perpendicular means at a right angle. So it gets a little bit interesting right here. So let's see if I can get this one up. I'm going to see if I can pull this one. Something froze there. So let's see. There's my other one, my first attempt. Uh-oh, I'm missing all of a sudden something here. Figures I had everything all set. I may have to know what I'm going to do. I'm going to just take this. That must have been while I was waiting for you folks. So I'm like jammed up here. Uh-oh, let me see. I'm jammed up in my PDF annotator. So I'm going to just move on. Let's see if we can. No, it's now it pops up. All right. No, it's not doing it. It's not doing it. All right. So I'm going to just move on to some other things that I have right here, and that's here. Let's see. I'm going to go back to sound. And when we do sound, that compression. Here's the guy you may have all seen, Mark Rober. He did that thing where people are stealing presents off of porches. He made a glitter bomb and with stink and things like that. But I want to show you this. Just I see I'm starting here at 4:45 in because I only want to see how long it takes for sound to travel versus like light. So right here, he has just a little air horn, and he built this massive horn, right, with just compressed air. So see how far away this sound can travel, and how I remember when I was about your age, maybe a little younger. My brother and I would go up on Long Mountain Road in New Milford, and we watched the fireworks in town. They were about 3 miles away, and we see the explosion of the firework. We'd count 1,001, 1,002, and we'd be counting like 20, and then we'd hear the boom. So that's what we can figure out the speed of sound. So there might be a ad that comes swirly. There might be an ad here. We're going to build one of these. So now this is what we're going to do. We're going to make something
Mr. Fletcher, I don't hear your sound coming through.
Oh, okay. I'm sorry. Let's see. Okay, let me see if I can. You still can't hear the sound?
I can hear it a little better. Maybe I might be the only one. Maybe it's me.
I can't hear the sound from the video.
Oh, it might be Mr. Fletcher. If you share on the top there.
What's that?
You have your sound going through when you're on the top of the screen there when you move your mouse up.
Right there.
Yeah, yep, I think so.
Super far away. I literally can't see it with my naked eye.
It's so far away. Like I can barely see it. It's right at the crest of the
now
hill.
the horn
There's
is
a little
right
tiny
here.
speck, and it's right there.
We're gonna do an experiment, and we're gonna test the speed of sound. We should hear it on this walkie-talkie, and then some amount of time later, we might be able to hear it from this distance. Lincoln's gonna measure the time on his stopwatch, and then we should be able to calculate from there what the speed of sound is. We're ready when you are.
So it's here, it's gonna be light. As soon as you hear that, so he hears it here. So he started. Now here it comes. It's coming down the desert. Right? It's coming just like me listening to the fireworks. It's coming down. That's crazy.
That's crazy! How long? It took 11 seconds for the sound of the horn to get you.
Now it's kind of interesting. I was talking to you about 331 meters per second at 0 degrees, and look, they did the math, and look what it is. It's 0.34 kilometers per second. And of course, if we multiply by 1,000, that would be 340 meters per second. So, and that's not quite 331 because it's warmer out, right? So that's interesting right there. I like that little demonstration right here. So let's see what else. I'm going to see if I can just get out of here and get this one more thing. I had a couple things I wanted to show you here with light. All right, when we first started this particular, virtual schooling, I had my students get out of the house and go out and do something. I called it my raindrop lens challenge. And this just happened to be me. I just happened when I first got my camera. I'm an indoor track coach, and I bought this fancy camera, and I was going to take pictures of them. So I'm a deacon at the church. So it was this rainy December day. I said, well, I'm getting, I was just really wanted to get going and taking pictures. So I'm practicing with my camera, and I'm pointing it at my church. But I didn't really care about that at the time. I just wanted to get a picture of this little tiny raindrop right here. And it was kind of interesting to see. Because as I zoomed in on it, I could see the whole church. You could see the church getting bigger and bigger, but inverted in that little droplet. So that was kind of fun to see as we got it closer and closer. And I had them do it, and I had students. They had to go out and make find a droplet, or they could use other liquids if they wanted. And you could see exactly what's behind it, upside down but inverted. So that was cool. All right, let me kind of clean up around here. Let me see here. This is going back. This is a physics interactive we use. This is called the physicsclassroom.com, and they have all these great hands-on things you can do. So a lot of fun here. I'm going to see if I get back to this. Let me see. I got to get back to where our regular desktop is, so we can get the desktop right here. Where's my desktop? Here. All right. Let me see here. I'm going to see if I can bring this up. Just stop sharing. And then I'm going to reshare. Sometimes if I do that, things happen to work a little better. Right? Let me see. All right. So I see. Any other questions people have with sound and light and the speed of sound and the speed of light? Well, let me see what I have here. I'm going to get out of the chat mode right here. Can you hear me right now, Andrew, or am I?
Yep, no, I can hear you perfect right now.
Oh, okay, great.
I don't have any questions yet. If any questions come up, either raise your hand or feel free to unmute and ask.
Okay. All right, so I'm going to go back here one more time so I can get here, share. And I want to get back to my desktop right here. And I want to get out of this. All right, I just want to get out of that guy. Oh, I'm kind of, my whole computer's locked up, so I'm sorry about that. I'm trying to get, this is because I had something special I wanted to share with you guys at the end here. I made up something. Let me see. Maybe I can get right back here. I can get out of here. Oh yeah, this is winning. This is locking me up. I was going to show you something here. It's too bad. But let me see. Andrew, if you can just chat for a second. I have to, I think, log off for a quick second, get right back on.
Absolutely.
Okay. Okay, here I go. I'm out. Here. Oh yeah, my whole thing's locked up.
No worries. So yeah, thank you everybody for joining us. Hopefully Mr. Fletcher can get right back on and get it working. But we hope that this kind of gives you an idea of what class might be like, if you are in an online situation at all next year. Hopefully we're here in person, but we use Microsoft Teams, and all of our students do have an iPad, so you'll have your iPad and you'll be able to use the Teams app to be in class, which is great. It's been a really good way for us to work this year. A couple of other random things. We are going to have a meeting next Monday, June 29th, or is it next Monday? 2 Mondays from now, sorry. June 29th at 7 p.m. with our athletic department. So if you're interested to come to that, we'll be sending an email out on Monday with our, sorry, I saw a hand raise here. We'll be sending an email out on Monday with a recording of this, but also with the sign up for the following Monday's athletics meeting. So our athletic director, Mrs. Mayer, will be there, as well as our fall coaches, to answer questions for you. Alex, I have a question from Alex. Nope. Okay, that must have been a mistake. Is Mr. Fletcher back yet? He's frozen on the bottom of my screen. Give it another 30 seconds. Does anybody else have any questions for Mr. Smith about chemistry, or what classes you'll be taking next year?
No, this all makes sense.
It all makes sense so far? Good. Perfect. We're going to have Mr. Fletcher and Mr. Smith started off, and we are going to have a campus ministry event after athletics, and then we're going to have a fine and performing arts meeting to talk to you a little bit about the different fine and performing arts options you have. And then we're also going to have a history lesson as well. So that'll be sometime in July. So we'll be sending you out a full schedule with sign up for those moving forward. But just to hopefully keep you guys engaged. And then, as the summer goes on, we'll be in touch about picking up your iPads and all those exciting things. I know that summer reading is almost ready. As soon as that's ready, we'll make sure it's sent out to everybody. Yeah. All right. I don't know if Mr. Fletcher is coming back or not. So I'm thinking, Mr. Smith, I'll let you make the final call. Do you think he's locked out on us?
I don't know. He might be. Yeah. Looks like he's still on the screen here, but
here he is. He's back.
Hey.
I'll apologize to everyone for having to listen to me talk the whole time. Mr. Fletcher, you're muted.
Can't hear you, Mr. Fletcher.
Yeah.
Oh, there we go. Yeah.
Well, what happened was, I had this already, I guess it was like locked up and things like this. But anyways, after all of virtual school this spring, now it happens. So here, let me share my screen. I just want to get rid of this here. Share my screen one more time. And I just hope I get this arrow. I want to just share one last thing with you. Let me see. I don't know. Oh, well, 2 things I'll show you then. Right? Can you see my screen now, Mr. Smith?
Yes, we can see it. Yep.
Okay, one of my final projects, I had the students, I had juniors, mostly seniors, and so we were trying to figure out other things to do. And I came across this on YouTube where people stuck at home are recreating famous paintings, and it's awesome. So there was a link to it. So people were doing like Mona Lisa and trying. So I said, I'm going to do this, but we're going to do this with famous scientists. So their job was to recreate a famous science photo painting from years past, from Aristotle to Watson, and select a scene, recreate it. And I was going to grade them on photo selection, the biography they do, background props, and it didn't matter, if you wanted to do a male or female, it didn't matter. So here's some of them right here. Neil deGrasse Tyson and Gigi Mahone, and they were so good, right down to the gold ring, the way they looked and their background, everything. And here's Holly Gustafson, who's doing anti-jump cannon. She and Charles Messier did the galaxies. They plotted galaxies and their brightnesses and locations. So she did a spectacular job. Now Felicia Link, she did Bill Nye the Science Guy. And it's kind of interesting, Photoshop, I hope, anyway. So that was one there. And then, I love this black and white contrast, these older pictures like here. And here we have Rosalind Franklin, right? Another famous woman, scientist with the DNA, right? Another one we had, here we have Chloe Lacouture's dad and used Thomas Edison right here. So this is a kind of fun, and here we have a couple other students, Jane Goodall, and using her cat instead of the monkey, and just a couple more to go. This one's kind of fun. Nolan Horn took, you've heard of Tesla, Nikola Tesla, and there he is in a Faraday cage with all these static electrical lightning bolts around, casually taken. So Nolan Horn said, I'm going to do the same. And you can see he did a great job, using Photoshop and making it look like that. So other Jane Goodalls, a lot of Jane Goodalls. I love, speaking of Tesla, here we go. Yep, you can see the resemblance right there. And another Edison, and very regal right here. So they had a ball doing it too. Kimani Campbell did George Washington Carver. So well done, from plant placement to all. Another Jane Goodall with Margaret Price. And lastly, we had two more here. Steve Irwin with Megan Shanley. And then I love what this student did here, how she put watermarks in here from Marie Curie, right? So they had a ball doing that. So let me see if I can get out of here without dumping out. So, hey, you get enough of all this. I made one little Team Northwest for you right here. So hopefully you can hear this. You hear that?
Yes, we can.
So there you are. That was you, class of 2024. All right. So,
well done, Fletcher.
Thank you. So I just want to say one last thing, get involved. We have robotics, music, Amnesty International, drama tours, plays, musicals, computer clubs, sports. You'll build meaningful, long-lasting relationships. So the more you get involved, the better off you'll be. It's a very friendly environment. The teachers are awesome. The students are even more awesome. And especially during this virtual school, they stepped up. Our students, every single one that I had one person tardy, and it was because of some Wi-Fi thing. And otherwise, it was a really great spring. I was really impressed with them all. So welcome, class of 2024. All the best to you. Relax this summer and get ready for the thrill of a lifetime.
Awesome. Hey, thank you so much, Mr. Smith, Mr. Fletcher. Happy Father's Day to both of you.
Hey, thank you.
Thank you very much. And everyone, I hope you all have a great night, and hopefully we'll see you on the 29th at the athletics meeting. If anyone has any other questions and you want to stay on for a minute to ask Mr. Fletcher or Mr. Smith, feel free. Otherwise, we'll see you soon. Thanks a lot.